Mr. Landlord.
Yeah?
What are you smoking, an army blanket?
Never mind about that. You owe me room rent.
All right, here's $28.
$28, fine. Just a minute. You owe me 13 weeks at $7 a week, and that happens to be a lot more than $28.
Well, that comes to $28.
Did you go to school?
Yes, sir.
Do you mean to say that you can prove that 7 times 13 is 28?
Well, it's gotta be. Certainly it is, because Mr. Rabbit and I, that's $28. That's what you get.
If you can prove it, I'll tell you what I'll do. I will give you the room rent for nothing.
You will?
But if you don't prove it, you owe me double the back rent. Is it a deal?
That's a deal.
Okay.
You happen to have any Crayola on there?
Crayola?
Never mind. I got it.
Oh, you have?
I got the Crayola. 7 into 28 is gonna come out 13.
That's your way.
That's my way. And it's gotta come out right. Now, first, I put down a 7.
Right.
Now, I'm gonna divide the 7 into 28.
Yeah.
I put a 28 there.
Okay.
Isn't that cute? Now, here we go. 7 into 2. 7 will not go into 2.
It will not.
That's a very big 7 to push into that little bit of 2.
As you say it is.
We ain't gonna hurt that little 2, are we?
Of course you won't.
So we take the 2, open your hand,
Yes.
and I put that 2 right there for safekeeping. But don't drop it and don't lose it. Now, 7 into 8.
Once.
Once, I put the 1 over here, 1 over there. Now, we're gonna carry the 7 because it's very big and it's getting heavy on my shoulders, and I'm gonna drop the 7 under there. Now, 7 from 8
Is 1.
is 1. I put the 1 down there.
Mm-hmm.
Now it comes. Would you mind opening up your palm of your hand, please? I would like to use that 2. Open it up. Give me that 2. You've had it long enough. I'm gonna put that 2 right there. Now, 7 into 21.
3 times.
That's right. 7 into 28. 13. Good enough?
Wait a minute. You have to prove this even better than that. You can prove it very easily by multiplication.
You mean you want me to emulsify it?
No, not multiply, multiply.
Emulsify.
Multiply.
All right. Multiply it.
7 times 13
It's
prove
28.
it. Go ahead.
Now, first, we got to put down a 13, right?
Right.
There's a 13.
Times 7.
Times 7.
Right.
7 weeks times 13, right? 7 times 3.
21.
21. 7 times 1.
7.
7. 7 and 1.
8.
And 2 to carry. 28. Wait just a
Now, wait a minute. I'm still not convinced. There's one sure way of proving this. One sure way, and that's by addition.
You want me to addition it up?
I want you to put 13 7 times on that wall and then draw a line and add them up.
You want me to put down 13 7 times?
That's right.
That's got to come out right. There's 1,
1,
2,
2,
3,
3,
4,
4,
5,
5,
6,
6.
7.
Wait a minute. What's the idea of spreading them out like that?
Well, it looks like a flock of seagulls going to hit the electric poles. Now we're going to add them up, right?
All right, go ahead.
Here we go. 3, 6,
Wait a
9.
minute. Let me do the adding this time.
Good. Come out right.
Well,
A 3, a 6, a 9.
Just a minute. I will do the adding. Then there'll be no mistake.
Yeah?
All right? $28 easy. All right?
Sure.
Now.
Go ahead. If you had it up, go ahead.
3, 6, 9, 12, 15, 18, 21.
22, 23, 24, 25, 26, 27, 28.
I should have wrote it on there, but fuck you.
All right. How's it going, everyone? I hope you're having all kinds of fun sitting at home on your asses playing video games for the past month and a half with COVID. But this is episode 5. Can't believe we got it to that point. In fact, you know what? We're going to just mark that. It's episode 5, and we're going to do this one under the title of What We Don't Know. There's good reason for it. Because, you know, when we're talking about the cataclysmic cycle, we're talking about the Earth noving or a cataclysmic solar flare, talking about the effect it would have on the Earth's rotation, as well as the orientation of its orbit and the orbits of the rest of the planets in the solar system. You know, you might just say, Scott, Tom, you're full of shit. So, and really that's because people have been trained to think a certain way. So what we're going to talk about today is what we don't know. We're going to talk about some of the things that you consider to be pivotal in your education, especially your scientific education. And we want you to realize it's okay to rethink things. It's okay to question that. It was Carl Sagan who said that science is a self-correcting process. And what he meant by that is really when you're talking about science, you have a hypothesis, then you research it to see if it lends weight to it or not, and you come up with a conclusion. Well, the conclusion that you should be coming up with is wherever the science takes you, not your hypothesis. Your hypothesis could be totally wrong. So keep on researching and see where it leads you to. Okay? So we're going to talk about what we don't know. And in particular, I'm going to talk about gravity. Okay? Because that has a lot to do with what we're talking about here. Or at least how we think things should be going. But really what we're talking about here is something totally different. But we'll get into that in a minute. Okay, so go back to 3rd and 4th grade. And what they taught you during that time was the person who discovered gravity was Isaac Newton. Okay? And we were taught that he was sitting underneath an apple tree and an apple fell on him and he thought, hey, what the fuck? What caused that? And he's the one that came up with the 3 laws, Newtonian laws on gravity. Okay? So we kind of think of him as the godfather of gravity. But really, gravity today in the scientific terms, we think of it in 2 different ways. One is we think of it as mean gravity, and I don't mean angry gravity. Mean gravity means simply this, and this is, in scientific calculations, is capital G, okay? But mean gravity simply means gravity as compared to the center of the earth. Okay? We can measure that. We can measure how much gravity's effect is from the center of the earth to wherever it is that you're doing it. The other way we talk about it is we talk about gravity in what's called the force of gravity. Okay? The force of gravity in scientific calculations is little g. Okay, but what we're really talking about here is the attractive force of gravity on mass, and that's calculated by the weight of the mass and the acceleration of the mass to mass bodies towards each other. Okay, the difference between that is Isaac Newton getting hit on the head with an apple versus having one thrown at him at full force.
Well, Brian, I've studied pie making, and the key is to find the absolute freshest ingredients. Therefore, we must go wherever and whenever they're to be found.
Where are we?
1666, England, home of Sir Isaac Newton and one of history's most famous apples. Which will be part of our pie. Ah! Gravity never happened!
So, the problem is, though, is we tend to use gravity as a constant in scientific calculation. And the truth is, it is not a constant. Okay? And we can prove that. Okay? Gravity is not a constant. You can't use one mean calculation of gravity and say that applies to everything in the universe. Okay? Why? Because gravity is related directly to the Earth. That's it. Not the sun, not the moon, not Neptune or Pluto or Andromeda. It's all calculated based on gravity here on Earth. And as you can imagine, it's different no matter where you're at. Okay, let me give you an example of that.
I'm not sure. I'm afraid we need to use math.
Alrighty. gravity at the Earth's surface is measured in meters per second per second. Okay, that is the force of gravity at the Earth's surface. Okay, this is what we use as our gravitational constant. However, if you get just 1,000, not a roux, 1,000 kilometers from the Earth, that drops down to 7.33. Okay, if you get 5,000 kilometers away from the Earth, the center of the Earth, it drops all the way down to 3.08 meters squared per hour squared. So the point is, this is not a constant. You cannot use big G as a constant without taking in a whole lot of other information in order to, I'm going to say it, fudge your calculations. Okay, so let me give you an example on something else of how that works.
You can't use the guy with the underbite because
Yeah. We'll put this back up. Episode 5.
It makes you kind of the underfoot figure. Just take these shoes, Morty. They're special grappling shoes. When you're wearing these things, these babies, you can basically just walk on any surface you want, Morty. Up, down, below, turn around to the left. These things really bring it all together. You have to turn them on, Morty. The shoes have to be turned on.
5. I'm going to apologize. This is my third beer.
what was this?
I have respect for beer.
Boom!
All
There
right.
it is.
Okay, so way back in the 90s, I worked in the oil and gas industry, and I went about 9 years in that industry at one site, and the refinery that I worked at burned to the ground. Along with the refinery, all the paperwork burned to the ground. As you can imagine, way back then, we didn't have a whole lot of computer technology. A lot of stuff was just written down, and that was our references. So I was given the responsibility of coming up with a spreadsheet that calculated the level of sulfuric acid inside of each one of our tanks. And each one of these tanks was about 40 feet tall by about, let's say 20 feet across. Okay? So I had to come up with a spreadsheet that would give us the ability to read in mercury inches a sight glass that would tell us what the level of this was at all times. So that means I was working with atmospheric pressure. Okay? So atmospheric pressure, we had it gradiated to tenths of mercury inches. So my calculations were great at 1 inch, but I kind of lost them at about a foot. Okay, why was that? Well, I knew the circumference of the tank, and I knew what kind of volume I had in there, but the problem is that I had all this weight of this fluid inside of here. So when I got to a foot, I had to add a fudge factor to the calculation. Okay, and I'm going to bring that up a lot. I had to add a fudge factor to it. That means I had to manipulate the calculation so that we could read at 1 inch and 1 foot and still get the right level. Well, the problem is, the higher I got up, whether it was 2, 3, 4, or 20 feet, every time I hit a foot mark, I had to add another fudge factor to it. Okay? So, all that's saying is that the calculations that science uses today has a lot of fudge factors in it. It has a lot of what we don't know. Okay? They get to a point to where they have infinities, and science hates infinities.
I'm not sure, I'm afraid we need to use math.
Meaning that it's a number that just goes on and on and on forever. Well, there's no precision in that whatsoever. So they have to add fudge factors in order to what's called renormalize it. Okay, well, that's really the way that science has continued on for 150 years. Even though we have people like Newton, who were grandfathers of a particular field, when it comes to the actual mathematics of things, they have to add in these fudge factors to eliminate infinities, numbers that will continue on forever. They want to be able to have some kind of prediction, predictability, so that they can say, okay, well, when you build an atom bomb and you use a certain amount of plutonium, you're going to have this amount of force. Okay, but because of the infinities, it was going all over the place. We'll get into that calculation, which is E equals mc squared, in just a minute. Okay, so the point is that going back to the calculations I had with regards atmospheric pressure. Okay, here's the deal. The numbers I was coming up were great. In fact, I actually won an award for all the maths at that particular refinery. Atmospheric pressure, however, or the calculations I had for this, were at sea level. Okay? Well, that's great. Everything that are designed, furnaces, air conditioners, there's all kinds of equipment that's out there that is calculated to work correctly at sea level. Well, when you get over here to Denver, okay, and Red Feather, where Tommy and I live, you know, we're sitting up here at 8,500 feet of altitude. Well, the numbers at sea level, which is 0, doesn't work at 8,500 feet. Okay, so you have to account for all of that. And really, having been in the industry where I had to make those calculations all the time for about, I don't know, 25 years, we add a lot of fudge factors in order to get things to work correctly at this particular altitude. Well, the same thing with gravity. Remember, what did we say? We said that the effect of gravity loses its strength the further away from the center of the Earth that it actually is. Well, now think about that. That means that gravity, even here on Earth, is going to be different, right? Okay, because we have all kinds of elevations. We have plains, we have sea level, we have mountaintops. Okay, we build little 4G or 5G systems now, okay, around the world. Well, what do you see there? You see different elevations. Okay, so gravity from the center of the Earth is going to be different here at the bottom of the ocean. It's going to be different here in the southwest. It's going to be different here in the Rocky Mountains. No matter how, it's all based on how far away it is from the center of the Earth. Okay? So in order to make things work, you have to put in a lot of fudge in order to get things to work at all these different altitudes. Okay? So, think about that. That means a lot of the things that we learned as being simple equations. I'll give you an example. E equals ms13. No, that's not right.
Those fucking guys, fuck them.
E equals mc squared. Okay? Very basic calculation. Okay? Really simple to understand. Everybody that's watching this has seen Einstein's general relativity calculation. The problem is, it only works in a particular place. Okay? Because what we're talking about is energy equals mass times the speed of light. Okay? Let's make that a proper G. Okay, beer. Okay, so with this particular calculation, there was a scientific paper came out of the University of Berkeley way back in 1998 when I first read it. And it helped me to understand that number, or that calculation is not correct. Okay, even Einstein had all kinds of troubles with this. Why? Because when we look at it as a bunch of constants. Energy equals mass times the speed of light. Well, here's one constant that's not constant: mass. Mass equals weight. Okay, it's a calculation of weight. Basically, it's the density of molecules in any given element. Okay, as an example, we are all made of carbon-12. Okay, that means that we're a molecule of carbon with 12 protons. Okay, with 12 subsequent neutrons. So carbon-12 is mass, yes, but there's all kinds of carbon. As an example, there's radioactive carbon, which is made by the sun, which is carbon-14. Okay, 14 protons. So the mass is the...
Son of a bitch, you.
Okay, I guess we're going.
Yeah.
All right, through the magic of television, we now have a whiteboard again. Okay, so I think I was talking about going back to my calculation of the amount of volume inside of these giant tanks, is that I kept having to add fudge factors in to my calculations as the level got higher and higher. Okay, that's because we were dealing with altitude. All right, so going back to that though, in atmospheric pressure, there's all kinds of things that make those calculations kind of worthless. Okay, one of them is temperature. One of them is humidity. Okay, because the more humidity that you have in the atmosphere, the different effects it's going to have on atmospheric pressure, meaning that your outcome, your predictability, is going to go way off. The other thing is, let's just call it dust. Okay, if you have a whole lot of dust in the air, it's going to change all of that. Well, the same thing with gravity. I mean, when you're talking about gravity, you're talking about the sun, the earth, the moon, the rotation of the earth around the sun, the rotation of the moon around the earth, and so forth. But what you don't realize is that you looks like you have a whole lot of empty space in here, but you don't. You have a whole lot of electromagnetism going around here. That's why we have these magnetic forces, the magnetosphere on the earth as an example. And so all of these different forces are going to have an effect on that electromagnetism, which means it's going to have an effect on gravity. So it's a matter of, no matter where you are at any given point, it's not just where you are in relation to the center of the earth, it's where you are in this particular atmosphere of electromagnetism. So gravity is not a constant. Okay, let's go back to E equals mc squared, something that we're all familiar with. mc squared. Okay, now what we're looking for is, if you want, again, if you want to have a plutonium bomb that blows up, you know, a city, rather than splitting the earth in two, okay, you have to have some idea of how much energy that bomb's going to put out. And so what you do is you try to calculate how much mass there is times the speed of light. Okay, well, here's the deal. The only constant in this particular calculation is supposed to be speed of light. And it is not a constant. We'll get back to that in a second. Okay, the reason is mass is not a constant, right? Because we don't know if we're dealing with C12, which is the carbon atoms that all humans are made of, or with whether we're dealing with C14, which is radioactive carbon that comes from the sun. Okay, we don't know what kind of mass we actually have. This 12 and this 14, what that is that's the number of protons in that particular molecule. Okay, here's the problem. We have a molecule here, nucleus. Okay, we have all these protons that are going around that particular atom. What do you see going on there? Those protons represent energy. Okay? It's energy that's going on there. So basically you're trying to explain energy with energy. Mass, each particular mass has its own energy. So what we learned way back in 1998 in that scientific journal from Cal Berkeley is that when you're doing this calculation, you actually have to use E equals M0, no energy. You have to remove the energy to do that calculation, times the speed of light. Okay, and they found by removing the energy that's going on in each one of those atoms, they were able to get a more predictable amount of energy. Okay, but here's the problem. Speed of light is not a constant. Okay? One scientific journal began its discussion on this, on the question of whether speed of light is a constant in this way. And I quote, "There are a number of senses to the meaning of this question. So there are a number of different answers." What does that mean? It means simply this. I don't know. Okay. Is speed of light a constant? I don't know. Sure, why not? Okay. E equals mc squared. There isn't a single constant in that calculation. Okay? This is what we're talking about. What we don't know. And what we don't know is we don't really know what the speed of light is. Okay? Here you have a galaxy system. Okay? And you're looking at a particular star here, but the Earth is over here. And so you're trying to calculate what's going on here, or how far away this is in light years. Okay? The problem is in between this galaxy and the Earth, you got all kinds of planets that are going on. You have electromagnetism that's going on throughout here. And light, as you know from anyone who ever worked with a prism, what does it do? It bends. Okay, and every time it bends, it throws your calculation off. So, is speed of light a constant? No, it's affected by the atmosphere that it has to go through. So basically what we're talking about here is that a lot of these scientific calculations that they use today have a lot of fudge factors in it. They make it up. And that fudge factors that they're using is what is commonly known as renormalization. Okay, put it into simple terms. How many of you watch the weather reports? Okay, so they take all this data and they put it together and they say that on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. On Wednesday, you're going to have clouds and possible storms, but on Friday it's going to be nothing but clear skies, right? But you wake up Friday morning, what do you have? It's raining outside your window. Okay, so now the calculation is clear skies with a chance of rain. Okay, they calculated the clear skies, but they had to add the chance of rain because they were renormalization. What they calculated was not what you actually got. This goes on in science constantly. And I challenge you to look up E equals MC squared. You will find it everywhere that it is not a real calculation.
God damn, I said it was a real calculation. I wasn't until... No, it was! Son of a bitch, you need some chicken, motherfucker told you. What the fuck? That's a real calculation. Man, I told you that many times. Shit.
Okay, it's math. Math is not physics. Okay, physics, blah. I need another beer.
Anyway, the underbite guy.
Uh-huh.
It reminds me of that. And then it also reminds me of doctors.
Yeah.
They do the same shit. Where it's like,
Yep.
oh, I don't know. It might be this.
Could be this,
here.
could be that.
Yeah. So, and what do we do?
Uh-huh.
Sure.
Sure.
Cool. We'll follow and just follow it.
Yeah, we'll
Just
pay
blindly.
you tens of thousands of dollars based on your hunch.
Yeah.
That's what we do with mechanics too, right?
Son of a bitch.
Yeah, absolutely. There is not a whole lot of constants. What's the point? The point of the episode is what we don't know. It's okay to question these things because they really don't know. It's a matter of they're taking their best guess, and I'm going to give them that, their best guess. Okay, they're learning more and more every single day. Okay, so why do we talk about that? Well, here's the deal. In the cataclysm cycle, we're talking about the sun, the earth. We're talking about the sun novaing. Okay, I'm going to draw it out this way. It's really circular. Okay, novaing, and then there's north and south pole energy release as well. And that has an effect on the magnetosphere of the earth. Okay? And what that's going to do, since the magnetosphere is directly related to the rotation of the earth, when it weakens and it comes to an end, or for some reason it is blocked or separated from the effects of the sun's electromagnetism, that it can stop rotating and start rotating the other direction, or it can stop its rotation and shift. Either way, it's going to be an amazing catastrophe. Now, I'll give you a great example. Here's something you can look up right now. We say that the Earth can reverse its rotation. Well, that's complete nonsense, right? Okay? Or we can say the Earth can shift, and now instead of it going from west to east in rotation, it goes south to north. That's preposterous, right? Okay, well, is it? Look it up. Venus. The rotation of Venus goes exactly the opposite of the Earth. It's in the same solar system. It's affected by the same sun. It's privy to all the electromagnetism that goes through the universe. But Venus is rotating in the opposite direction. Okay? Tommy loves this one. Uranus.
I love it.
Okay? Uranus rotates at 90 degrees. Okay? So, is it crazy to say that the Earth can stop rotation, shift, or reverse rotation? No, it's already happening on these other planets. So, again, they don't really know. It's okay to question it. You can't take their advice or their claims that everything's okay, there's nothing to look at here. Okay? They don't fucking know. Okay, the solar system proves that it's possible. The geology that we've talked about, the history that we talked about, the mythology that we talked about, all show that that's what's happening. I'm colorblind. So, we think about it. Where am I going with this? Okay, so let me give you an example. Gravity, again. And you're all going, oh, don't talk about gravity again, my
I don't know
eyes."
what it is. I'm
I don't
scared.
know what it is. That's okay. They don't know what it is either. Okay, so let's talk about gravity for a second. Gravity is considered by science as an attractive force. Okay, an attractive force. That means that the sun has a gravitational pull on the Earth, and that's what's creating these orbits of the Earth around the sun. Okay, to make things better for Tommy, we'll color the sun a little red.
Oh, there you go.
Okay.
I love it. That's very good. Now I get
Alright.
it. Sorry.
We might as well make the Earth a little green, right? Okay.
Blue.
And a little blue, yeah. We'll do the atmosphere. Okay, so think about this. Gravity is what we consider what keeps us here on the Earth. It's what keeps us from flying off into outer space. Every time we think about gravity, we think about how it pulls us in, it keeps us stable. All right, but think about this. If gravity is an attractive force, what's keeping it from being sucked right into the middle of the sun? Okay? It rotates around the sun, right? But if the sun is always pulling on the Earth, eventually that orbit will decay and the Earth will end up in the middle of the sun. So there has to be something else. There has to be something that is both attracting it to the sun and at the same time forcing it away from the sun in order to make the orbit stable. We've been told our entire lives, oh, well, the orbit is due to gravity. Well, it can't be. That's impossible. There's no fucking way that the Earth won't crash into the sun or the moon into the Earth. It's just impossible for that to happen. There has to be something else that is going on that they're not talking about or that they don't know about.
We produce the target. Can I float a ball on a magnetic field in the same way that I floated the ball on the water jet? Well, here is a ball. It's made of aluminium, and this is going to act as our jet, a single coil which is going to carry alternating current. I switch it on. The ball is certainly trying its best to float. But you see what's happening? It's like trying to balance a pencil on its point. What we need is some inward force which is going to make it drift back every time it tries to get off center. There seems to be no equivalent of the surface tension we had with the water jet. Now inside this coil there is a second coil, and I'm going to feed this with alternating current of a different phase so that I can produce an inward traveling magnetic field which I can detect with our rotatable cylinder. Notice that the bottom of the cylinder is always moving inwards. And now when I replace the ball, it does. Now it's one thing to float a ball as big as this. But what sort of apparatus should we need to float a ball this size? It's a different world, you know, from the world of ping pong balls. Barry, if you just come and take the ball back slightly, we can see what we've actually got. Now this is a sort of exaggerated version of the small ball coil. The inner coil is set down deeper in relation to the outer. First of all, we're going to send current through the outer coil only, as we did before. Would you like to come on the switch, please, Jim? Now, Barry, you and I have got to catch it, otherwise it might damage itself by falling back. Ready, Jim? 3, 2, 1, on. Right, lower it, Barry. Let's try and balance it. Off, Jim. Again, it isn't stable with a single coil. Could you connect the other coil, please, Jim? Now, would you take the ball away, Barry, please? Now, I'm going to check the phase sequence of the two coils using a rotatable cylinder, which I've used before. What I want to happen is the magnetic field to go down the outside of the cylinder and so rotate it in that direction. So I want to see the cylinder spinning that way. Switch on, Jim. Switch off, Jim. That is the correct direction. Now, Barry, if you could have the ball, please. Now, this time, it shouldn't drift off. This time, you should fairly be able to see the magnetic flux spraying off the sides like you did the water from the ping-pong ball. It might even spin for us. You can never tell just what this ball's going to do. If it spins, then we shall indeed have come full circle in the circle of magnetism. Ready, Jim? 3, 2, 1, on.
And I believe that is what's called Birkeland currents. Okay, we have a couple videos that'll help explain that.
We introduced a potential scientific breakthrough that could have profound implications for all of cosmology, eliminating the perceived need for dark matter. In recent years, retired professor of electrical engineering Dr. Donald Scott has composed an original modeling of the structure of a Birkeland current. The visual signature of the Birkeland current is counter-rotating cylinders, which are clearly seen in the earthly auroras, at the north poles of Jupiter and Saturn. And as seen in these recent images, even at the poles of Neptune. In the electric universe, Birkeland currents flow across interplanetary, interstellar, and even intergalactic space, organizing material across the vastest cosmic distances. In a new scientific paper entitled Birkeland Currents in Dark Matter, scheduled for publication in April of this year, Dr. Scott proposes that his model of the Birkeland current may finally help explain anomalous stellar velocity profiles, with no need for dark matter. In this episode, Dr. Scott summarizes his new paper, beginning with a review of his previous findings on the Birkeland current structure.
As most people who've seen space news realize, I was fortunate enough a couple of years ago to develop a model for the so-called Birkeland current. The Birkeland currents, just to bring everybody up to speed, is the shape that the clouds of charges that emanate from, well, one example is that emanate from the sun and that go down into the North Pole and the South Pole of Earth to create the aurora borealis and the aurora australis. That's the Birkeland current. And, there's a lot of talk these days about the fact that these Birkeland currents, huge versions of them, not the kind that just go into the North Pole of Earth, but the kind that actually feed galaxies, are feeding galaxies, and galaxies are forming in strings. Those strings are Birkeland currents. And so we know what the velocity of rotation of those galaxies are. I think I've included a picture there of M33 galaxy, and there's a graph of the velocity in kilometers per second versus the radial distance out from the center of the galaxy. And so I made an assumption. Now, it's a big assumption, it's a big if, but if I'm right, and if Birkeland currents do feed those galaxies, the galaxies form on those Birkeland currents due to the Z-pinch effect, then you can look at that curve and you say, hey, that's the velocity. I know what the velocity is. It begins as the yellow curve from starlight, and it continues on from the 21 centimeter hydrogen data that goes out. But it looks like the velocity goes up very quickly as you move out from the center of the galaxy. And then it doesn't slow down, it keeps getting faster, but it gets faster at a very slower rate. And that's called the stellar velocity profile of a galaxy. And that's been measured for decades. Well, the problem is that the people who looked at that first were Fritz Zwicky and Jan Oort. Looked at these curves, this one's very much like this, and said, oh, that's not what Newton's laws say should happen. On that curve, you see there's a dotted line, and it says this is expected from the visible disk. Well, this is what's expected from Newton's laws. The velocity should get lower with increasing radius, not higher. Well, that was a big puzzlement, and so astronomers at least began to publish papers, and they all settled there's invisible matter out there that's changing the equation, and there's really more mass out there than we thought. If you include this missing invisible, somebody named it dark matter, then that curve will be as we measured it there, that one that continues to increase with radial values. Make a long story short, these guys, these astronomers, have been hunting for this dark matter for 85 years. And there's been experiment after experiment after experiment to try to find the dark matter that gives it that stellar profile of M33 a rational explanation. And they haven't found it. They've come up with strongly self-interacting dark matter, repulsive dark matter, self-annihilating dark matter, fuzzy dark matter. Well, it goes on. It's ridiculous. They don't know why Newton's laws don't work in those galaxies. And there was a fellow by the name of Matti Milgram. He came up with the proposal we have to modify Newton's laws. That's not true. In real science, if you do 24 experiments and they all fail to give you the answer you think you're looking for, there's one thing you can do and only one thing you can do, and that is to throw out your hypothesis and come up with another hypothesis.
But you'll find that it is impossible for gravity alone to create that.
I got something. So.
Do you want a different color?
No. Well, actually, it might work better. and it might fuck you up a little bit. So, if you go here, you got this bigger one. Nancy Reagan.
All right. That's funny.
God damn it.
Two drunk guys teaching science. This is awesome. This is why we got to keep that going. Okay, so we're going to talk about Birkeland currents in the video. Okay. Okay, let's talk about, NASA. NASA should be the ultimate authority on gravity, right? And we look at all kinds of sci-fi movies, 2001, Interstellar, and so forth.
Star Trek, shit.
Yeah, and it's like...
Are we ready to spin?
Just a second.
All right, let's do it. % of spin. 1G. How's gravity treating you back there?
Wow. Romley? Hey, you okay?
Yeah.
You alright?
Yeah, I just need a minute.
Okay, I think we have some Dramamine in the hab pot. I'm just gonna go get that. Oh. Might be in the cryo bale. Just be a sec.
Hey, Brian?
Yeah.
Bring a lot.
Yeah, and it's like they've mastered gravity. They get on these big space stations and they're able to walk around and do normal things even though there's no gravity in space. But any reputable scientist will tell you there is no such thing as artificial gravity. Why? Because they don't know what the fuck it is. Okay? Let me explain.
Dang it, you got a fucking thing in
Yep.
that erase. Okay.
How many of you have ever been on that little thing in a playground where you all get on it and it's got all these handles on it and you keep trying to get it going as fast as you can, what's going to happen? Well, the fat kid is going to get really sick. He's going to fall off and he's going to throw up in the playground. Okay, why? Motion sickness. Same thing happens with a space station. They found that if they spin this thing too fast, that the astronauts start getting sick. So what they ended up having to do is they had to take that rotation and they had to break it down to no more than 1 revolution per hour. Okay.
Really fast.
So that means the space station had to rotate so slow that it would take a whole hour for it to get there. Okay, it would still create, the centrifugal force and everything, but if they did it any faster than that, the astronauts were getting sick. Okay, here's the problem. It's all about size, right? It's always about size.
Yeah, that's what she said.
Okay. So what they realized is that they would have to create a space station that was 2 kilometers wide in order to get 1 revolution per hour. Well, okay, so make one that's 2 kilometers wide. That's a lot of money. That's a lot of materials. It's a lot of materials to get off the Earth, up into the space station, spend decades building it in order to build a space station that would handle this so your astronauts didn't get sick. So, the point of the matter is, artificial gravity is, you can say it, bullshit.
Yeah.
There's no such thing. Okay? So, what's the point? They have no fucking clue what gravity is. They can't create it. They can't reproduce it because they don't even know what it is. They don't understand that how it works, why it works, how strong it is. It's all a bunch of fudge factors. Okay, however, this will explain the orbits a whole lot better. And if you can master this, which is the push me pull you of magnetism, then you will have the ability to do those kind of things that they were trying with artificial gravity. And I think that's it.
I had an idea.
Okay.
I'll just keep rolling because I'm retarded.
Go for it.
So, what you're talking about, so even if the space station was like a round thing, and they got it spinning in this direction, what if they had something on the inside that was going this direction? Something in the center that was going that direction. So where they could even out.
Exactly.
Like super magnets.
Yep. And you know that's such a simple explanation, isn't it?
Yeah, well, it is.
You just described Birkeland currents.
Sure.
That's what a Birkeland current does.
Right. Yeah. But I'm just saying, why not?
Yep.
Anyway.
That's the only way you can do it.
That would be the only way.
You solve this equation. You solve this equation, now all of a sudden you understand how flying saucers work.
So it'd be like
you would now understand anti-gravity.
Equals M bullshit.
Correct. E equals N times bullshit.
Oh, sorry.
No, you're... Exactly. Oh.
Beer break. Oh, yeah, sorry. Beer break. Take number 12, bitch.
Oh my God, Morty, what did you do? You killed the Simpsons, Morty!
No, I didn't mean to.
Oh, God, look at the baby one. Oh my God, Morty. You killed the entire Simpsons, Morty. They're a beloved family, Morty. They're a national treasure, and you killed them.
I'm just a kid. I'm just a kid. I don't want to go to jail.
Relax, Morty, calm down. We'll take care of it. Okay, I want you to take that vial of Simpsons goo and this picture to this address. They'll make us new Simpsons. You understand me, Morty?
Me? What are you gonna do?
Morty, I gotta clean this place up before somebody comes snooping around. You know how many characters there are in The Simpsons, Morty? There's like 1 billion characters. They did an episode where George Bush was their neighbor.